Great. Okay, so that's good. Let's review what we learned last class, right? So we're still working on this dispersion propagation, right? We're still working on this dispersion propagation. We have 3 legs, right? First one is just the Fourier transform, and second one is the propagation, the dispersion propagation in frequency domain, right? Just a factor. And then we take the inverse Fourier transform. So we still have the notes from the last class. This is the step we take the inverse Fourier transform, right? We take the inverse Fourier transform. Remember that this UZT omega is this piece, right? UZ omega is this piece. So this is U hat Z omega. We take an inverse Fourier transform so we can get UZT to get this step, right? If we further look into this UZ omega, remember that this piece, right? Exponential half I K naught double prime Z omega is the dispersion, right? Dispersion factor. It's that cause the delay, cause the phase delay for different phase delay at different frequency. That's why you get pulse broadening, right? That's why you got pulse broadening, okay? So we get this, we take the inverse Fourier transform. It's a rather actually complicated integral, but we have a table, right? We can use the integral table and we get this result. And the full picture or the full wave is actually pretty complicated, but we can analyze the real part or actually the absolute value, right? The envelope. So the real signal, the oscillation, it looks like this, right? But we can look at this envelope. The envelope is, we can take, split the real and imaginary part, right? So we have this factor, right? This numerator and denominator. Denominator has an imaginary part. So we multiply T naught plus I K naught double prime Z, right? So we have X minus Y times X plus Y. We got X squared minus Y squared. And this Y has an I in it, right? Y has this I in it. So we got I squared is -1. So we get X squared plus this X squared, the T naught squared plus K naught double prime square and Z square, right? In the numerator is T naught square plus I K naught double prime Z. So we multiply this factor in both numerator and denominator, so we can remove the imaginary part in the denominator, so we can separate out into 2 pieces, right? So this is real part, imaginary part. We take an absolute value, this exponential, let me write this exponential I theta, right? Absolute value square is 1. Right? Exponential I theta. Why? Because it's cosine, right? Cosine theta plus I sine theta. So this is basically cosine theta square plus sine theta square. So we get 1. We get 1. Now we only look at the envelope. This is the result, right? So we take A square, T naught square, this bunch of stuff. It's the square root. Now it's we remove the square root and take absolute value square. This 1/2 removed, right? 1/2 removed. So it is square. So 1/2 cancel out. We only have negative T square over T naught square plus K naught double prime Z over T naught square. Right? Okay. So this is the pulse. at here, right? At here. So we take a long way, right? We take the Fourier transform and then dispersion propagation, right? This factor, dispersion propagation, takes the inverse Fourier transform. We got this. Any questions? Okay, so we are good, right? So that's the result we have. We got the result. Let's remove everything we have. We don't need this anymore, right? But we will. Okay, now what we have is this equation, right? This equation. Instead of analyzing the amplitude, right? We only look at the pulse width. So how would this pulse width vary as you propagate along the fiber or a waveguide? So we can see it is still the Gaussian, right? It is still the Gaussian. T is the variable. T naught is the initial pulse width. K naught double prime is a fixed number, and T naught is a fixed number. As long as your initial pulse is determined and the dispersion in the fiber is determined, this is all determined. Z is the propagation, right? So it is Gaussian, but for different Z, we have different Gaussian function, right? Different Z. So let's now take so T naught Z, right? We have a new T naught. Previously, we have a Gaussian function, exponential negative t squared over t naught squared. Now we have t naught z. Instead of t naught squared, it is now the whole thing, right? So t naught z squared equals t naught squared plus k naught double prime z over t naught squared, right? T naught squared, okay? Okay, so this is my T naught Z, right? So basically, if the Z is 0 at the beginning, it is T naught squared. Once you propagate, when Z increases, the whole thing increases. That means the pulse width broadening, right? Pulse width broadening, because it's squared, so it's always positive. So T naught Z always increases, right? T naught Z always increases. So let's look at T full wave half maximum, right? T full wave half maximum and Z, right? T full wave half maximum Z is the 2 nature log 2 and half, right? 2 nature log 2 and half, right? And then this is T naught square plus K naught double prime Z over T naught, right? Square root. Because we take a T naught, we take a square root, this is T naught, right? So it's the square root. This piece is the T naught Z. And we need to convert this T naught to the full wave half maximum. Remember, this is the factor we did on converting, right? So we have an exponential function and how to find the full wave half maximum. How to find the full wave half maximum. Right? Okay, so in this case, the T naught is that, and then this is basically T naught full wave half maximum. Okay, so let's remove this T naught, right? So let's remove this T naught square, move out. So it becomes the 2 nature log 2, 1 over 2 T naught, and then take bracket 1 plus K naught double prime Z over T naught square, right? So it should be the T naught square. T naught square, and then take a square also, and the square root, right? Yeah, okay. So I extract the T naught out. I extract T naught out of this bracket. We have T naught, and then we need to have this T naught square, right? T naught square. Okay, so now with that, this piece, if we look at this piece is the full wave half maximum, the original full wave half maximum, right? So this is the original T naught, this is the original T naught full wave half maximum. Original T naught full wave half maximum. This is the original one, right? This is the original one. So let's actually rewrite it. So it's the T full wave half maximum 1 plus K naught double prime Z over T naught square, and take a square root, right? Take a square and square root, right? Okay, let's further simplify it by, so this T naught double prime and T naught square is a constant, as we previously learned. Once we have a pulse there, once we have a waveguide, it is determined. So let's rewrite it as T full wave half maximum 1 plus LD over Z, and then take a square root, right? Take a square and a square root. Okay, so now that's the story, right? That's all the story. So we have the Z over LD square. What is LD? LD is called dispersion length. It is, in this case, it is T naught square over K naught double prime. It is dispersion length, right? It's the dispersion length. So in other words, we can quantify this dispersion by dispersion length. It is depends on what is the pulse width at the beginning and what is K naught double prime, which is the dispersion parameter, right? Dispersion parameter. So the pulse is broadening by a factor of 1 plus Z over LD square, and 1 over 2, right? 1 over 2, well, square root. Questions? Okay. Okay, so we can look at this. This is the pulse shape, right? So the pulse that initially, so we can say this is a pulse that is initially narrowest, spread fastest, because their bandwidth, right? So let's say if we have a broadening, if we T naught, right? If the T naught is small, that means initially they have a narrow pulse. If initially it's a narrow pulse, then LD is a small number. So LD is a small number. Overall, it will be the T full wave half maximum increase faster or slower? So let's do chart. Let's have a vote, right? So do we have a chat box? Where can we use a chat box? Yeah. So can you actually write it down? So if we have a small T naught, if T naught is small, will T 4-wave half maximum, is that going up or down? It increases fast or slow? So let's use chat box, whether it is an increase slow or fast. The T 4 will have maxima. It will increase fast. Thank you. Who else? Fast. Thank you. Who else? Okay, great. We get fast. That's good. At least we get 3 fast. Okay. So now the reason is that we have the LD T naught is small, so it's in the denominator, right? If we have small denominator, that means everything is big, right? So it increased fast. But why it increased fast? The reason is that if we have a narrow pulse, right? If we have a narrow pulse, then we will actually have a broad bandwidth. We have a broad bandwidth, right? So if we have a narrow pulse, then we have a broad bandwidth. And if we have a broad bandwidth dispersion, right? So here and there. So you have different frequency. You have a different frequency. One is propagating faster than the other. But if we have we have dispersion, right? It's 1 picosecond per nanometer per kilometer, right? 1 picosecond, it's a negative 1 picosecond per nanometer per kilometer. If my spread out, if my pulse in spectral domain is well spread out, that means it is actually broadening. It is usually, for example, in the first case, we have narrow. We only the delta omega is only 1 nanometer. So I shouldn't say delta omega. I should say delta lambda is 1 nanometer, right? And second one is delta lambda is 2 nanometer. So if I have a broader spectrum, my dispersion actually have more severe impact, right? Because broad bandwidth is wider. So altogether, the whole thing has more severe effect. So that's because their bandwidths are larger. And they suffer more dispersion. So, and let me use pulses, right? It's actually pulses. Pulses that are initially narrowest spread fastest because their bandwidths are larger and they suffer more dispersion, right? So that's what our calculation tells us, right? So because once we have initial T naught is narrow, bandwidth is wide, so they suffer more from the dispersion effect, right? Okay, when Z is small, right, at the beginning, this width growth is quadratic. Z is large. So when Z is small, this is quadratic, right? So it's the Z square, right? Because once this is a small, this 1/2 can fall down, right? So remember, if I have a 1/epsilon square root, and epsilon is small, we can approximately equal to 1 plus half of the epsilon when epsilon is small, right? When epsilon is small. So if epsilon is large, right? If epsilon is small, 1 plus epsilon square root equals approximately equal to 1 plus epsilon over 2. If epsilon is large, right? If epsilon is large, do I have? Let me finish it. If epsilon is small, right? If epsilon 1 plus epsilon square root approximately equal to epsilon square root, if let's say less is small, much less than 1, if epsilon is much less bigger than 1, right? If epsilon is much less than 1, then 1 plus epsilon square root equals 1 plus epsilon over 2. If epsilon is much greater than 1, because so 1 is negligible, right? 1 is negligible, so it's epsilon over square root. So in this case, if Z is large, 1 is negligible, then growth is, we take a square root, it's linear. Right? Growth is linear. Okay? Okay, growth is linear. Right? Right? So we have two different regions. At the beginning, growth is quadratic because it's 1/2, right? Z square over LD square over 2. So it's quadratic. And then Z is large, growth is linear, right? So it's more or less, it looks like a function. We're going to look at it. So it's like this, right? At the beginning, it's quadratic, and later it's linear, right? So this is the T4 with half maximum, right? This is Z. So that's how pulse will broaden, right? Pulse will broaden. Okay, let's give a specific example. Let's give a specific example. Here's this is the LD over Z, right? So let's say T4 with half maximum and 0 is 20 picosecond, right? 20 picosecond. And let's say D is -1 picosecond per nanometer per kilometer, right? And we have and then we calculate, right? We obtain, so from this T4 we have maximum, we can calculate the T0, right? We already got it from previous class. It's 12 picosecond, right? And then this K0 double prime, right? This K0 double prime, we can calculate from this D. We already did it. K0 double prime is 1.2 picosecond square over kilometer, right? Over kilometer. Okay, so that is the calculation. It is only valid for lambda equal to 1.5, right? So we already find it. So now with that, we can calculate the LD, dispersion length. So T0 is 12 picosecond, K0 double prime is this, right? Oh, let's actually add a, because there is a square, let's add an absolute value, because k naught double prime sometimes could be negative, right? It's the negative dispersion. So here, remember this d is negative, k naught double prime, and d has a flipped sign, right? Okay, but because dispersion length is always positive, so let's use a square root, square absolute value. Let's use an absolute value for k naught double prime. Great. Now let's say at z equal 100 kilometer, right? Let's look at the 100 kilometer, right? So if we look at the LD, right? So LD is roughly this T naught prime, right? T naught prime is 12. So it's the 140, right? 144 divided by K naught, so 1.2. And then so picosecond cancel out. So then kilometer will go up. So this in this case, the LD is approximately equal to 100 kilometer, right? I mean, you can calculate, but it's roughly about 100 kilometer. So at the 100 kilometer, T4 with half maximum, T4 with half maximum, right? We can calculate. So this is the 4 with half maximum plus z over LD squared, take a square root. So let me just write it down, 26 picosecond, right? 26 picosecond. And then z is 200 kilometer, and then this T4 with half maximum is 39 picosecond, right? So we get z equal to 500 kilometer, and then my T4 with half maximum, right? 4 with half maximum is 86 picosecond. Okay. So that's how we calculate. That's how we calculate the 4 with half maximum. That's how we calculate the 4 with half maximum. So we gone through quite a lot. We start from the U 0t to 0 omega, and then we calculate dispersion. Then we come back to the in the time. Right?
Dr. Hill?
Yes.
I have one question.
Yeah.
The formula you're using for T4 with half maximum is at the bottom right. Is that supposed to have an equal sign, or?
Yeah.
So it's supposed to be
half maximum, but the z dependent should be this.
Okay. Okay.
Yeah. So it's T4 with half maximum,
Yeah.
z equal to T4 with half maximum, 0 actually, right? So it's 0 times 1 plus z over LD square, and then take a square root.
All right, thank you.
Okay, great.
Sure.
Great. Okay. So that will give us the whole picture, right? So it's broadening, and it is more broadened at the beginning. It's increased by twice. It's not actually increased a lot, but later it's more like linear, right? It increased by a linear, and we're in the region of linear growth. So this is still roughly about 1 kilometer. So at this region, it is still kind of quadratic, but once we above 500, so let me write it down. So we are about, so we are in the region of linear growth by z equal to 500 kilometer, because this z at 500 kilometer is way bigger than the dispersion length of 100 kilometer, right? 100 kilometer. In other words, when we understand it, is that once the length is less than dispersion, right? Once this length, once this LD is Z is way less than LD, once the propagation distance is way less than LD, the broadening is almost negligible, right? For example, 1 plus 0.01, it's almost no impact, almost has no impact. So we can use this LD as dispersion length to characterize the dispersion effect. Once this Z is approaching this LD, then we can see some broadening. But if the Z is way less than LD, we all see negligible broadening. Right? We see negligible broadening. Okay. Questions? Okay. So now we get an analytical solution for the Gaussian pulse, right? For Gaussian pulse. Gaussian is actually a nice pulse shape. Gaussian is a nice pulse shape, right? Because we can take a nice integral. We can take a nice integral. In reality, in some laser, right? Some of the laser, the output is not actually very nice Gaussian shape. Instead, they have a lot of different shapes, right? Instead, they have a lot of different shapes. For example, we have parabolic secant shape, and we have super Gaussian shape, right? So we will actually look at the super Gaussian shape and the hyperbolic secant shape. But the integral is really difficult. So instead of numerical analytical solution, we're going to use MATLAB to find out what kind of dispersion effect it will play with different type of shape, right? So it's nice to use MATLAB to use numerical method. Okay. And then this pulse, once we have this dispersion, right? So it becomes a chirped Gaussian pulse, right? So we have Z and ZT, UZT. This is the pulse, right? So this is the pulse, UZT. This is A T naught over T naught squared minus IK naught double prime Z, right? And square root, and then exponential negative T naught square over, no, not T naught square, it's the T square, right? T is time variable. And then this is 2 T naught square minus I K naught double prime Z. Okay, minus T square over 2 T naught square minus I K naught double prime Z. Right? So this is the pulse, right? What this is right here, we take the Fourier transform, propagate dispersion, inverse Fourier transform. This is called chirped. It's called chirped Gaussian pulse, right? It's called chirped Gaussian pulse. What happened is that it has a chirp. Chirp means time dependent of its instantaneous frequency. So it's time dependence of instantaneous instantaneous frequency. Right? Time dependence of instantaneous frequency. Right? So we will have up chirp. We will have up chirp. So that means my pulse has an let's say up chirp, meaning that instantaneous frequency rises with time. Instantaneous frequency rises with time, right? So up chirp, meaning that instantaneous rises with time, and down chirp. Down chirp, meaning that it's instantaneous frequency decreases with time. So it is the instantaneous frequency rises with time and instantaneous frequency decreases with time. So it's up chirp and down chirp. Let me draw a picture with you, right? So I have a pulse. This is my envelope, right? So what we have is, so we can have this, right? So in other words, I'm drawing this picture as a quite exaggerated picture. So we have at the beginning, the frequency is small, right? So, excuse me. Later on, the frequency is increases, right? As function of time. So this is up chirp, right? This is up chirp. And you can draw, of course, the down chirp. It's the opposite way, right? So in other words, once we have the dispersion effect, what we have is a chirped Gaussian pulse, right? What we have is a chirped Gaussian pulse. We have a chirped Gaussian pulse. Okay. Okay. So once we have this chirped Gaussian pulse, we can also write, or we can also write a a function. So representing a chirped pulse by U representation. We can also write this as U0 T as exponential negative 1 plus IC over 2, and then T square over T naught square, right? T over T naught square. So this is the complex number in the denominator. We can rewrite this expression by the complex number in the numerator, but they're the same thing, right? It's just a way. So one usually use this expression to represent a chirped pulse. One usually use this representation to represent chirped pulse, right? Because it's you want to write some constant minus C, you can also write 1 plus IC, right? C could be positive, this C could be negative, right? So we have C plus 0, that means it's up chirp. Then C less than 0, it's down chirp, right? C greater than 0 is up chirp. C less than 0 is down chirp. Okay. Okay. And then we have Now so we can have we can put sometimes those laser, right? Those laser output has a dispersion. So when the laser pulse coming from a light pulse coming from a laser, they might be chirped, right? They might be chirped. So once we put this into a fiber, depending on, in other words, you have positive dispersion or negative dispersion. In other words, if you have a pulse, right, in frequency domain, and you have omega 1, omega 2, and sometimes omega 1 can propagate faster than omega 2. Sometimes omega 2 can propagate faster than omega 1. Or omega 2 can be slower, right? Omega 2 can be slower. So depending on which one is fast, will have different effect, right? So in other words, when K naught double prime C is greater than 0, right? The chirp factor and the dispersion in the fiber is greater than 0. A chirped Gaussian pulse broadens monotonically will broaden monotonically, all right, at a rate faster than unchirped. At a rate faster than unchirped, right? So when K naught double prime and C and they are in the same dispersion category or the same dispersion effect, a chirped Gaussian pulse broadens monotonically at a rate faster than unchirped. In other words, at the fiber will make them different frequency, propagate different speed. But in the initial pulse, when at the laser, at the input of the fiber, they are at different frequency, they already have a different shift, right? They already chirped. So it will make it worse at a rate faster than unchirped. So when K naught double prime and C less than 0, their contribution is the opposite, right? A contribution is the opposite. The pulse width initially decreases, then increases. The pulse width initially decreases, then increases, right? Then the pulse initially decreases, the pulse width actually, the pulse width initially decrease, then increase, right? Meaning that once I have some kind of chirp or dispersion in it, but my propagation just compensate this chirp. And so initially they will decrease, but later on they increase, right? Initially decrease, later on they increase. Okay. There are different names. It says, so K naught double prime is less than 0, or they are totally opposite, right? The larger than 0 is called anomalous dispersion. Anomalous dispersion, right? And when K naught double prime greater than 0 or D is less than 0, it's called normal dispersion. Normal dispersion, right? It's called normal dispersion. So K naught double prime is greater than 0, and D is less than 0. It's called normal dispersion. So it's just a way you quantify the type of dispersion. Questions here? Okay, so let me see. We have different pulse shape. Sorry, I erased kind of fast. Another type called hyperbolic secant pulse. Right? So it's from some mode lock laser. Mode lock. So it's some mode locked laser. Right? So the U0T, it looks like a secant shape. Secant shape T over T naught, and then exponential negative IC T over 2 T naught square, right? So this secant shape, X is 2 over exponential X plus exponential negative X. So this secant shape is defined as 2 over exponential X plus exponential negative X. Okay. Then we have super Gaussian pulse. It's super Gaussian pulse, right? Super Gaussian pulse. This pulse representation is that this is the U0T as exponential negative 1 plus IC over 2 T over T naught 2M. Right? So in other words, this is U0T exponential. Usually the Gaussian pulse is just 2, right? But now we have 2M. So it is, instead of the Gaussian pulse like this, it looks usually, it is something like a, more stepped, right? Stepped pulse. Because it has a 2M, right? So it has a square of quadrant of 6, 4, 6, 8, right? So that's why it fall off more rapidly compared to the normal Gaussian function, right? Okay, so the M is 1. This is the M is the 1 is chirped Gaussian pulse, right? Here, if M is 1, that is chirped Gaussian pulse, right? So M is 1. M is the order, right? This is M is order of super Gaussian. Of super Gaussian, right? M is the order of this super Gaussian. So this is a super Gaussian. So this is a pulse. This super Gaussian is a pulse with steeper leading and trailing. Leading and trailing edge, right? Leading and the trailing edges. A path with steeper leading and the trailing edges broadens so broadens more rapidly with propagation. Because such a pulse has a wider spectrum to start with. Because such a pulse has a wider spectrum to start with. Right? Let me read. A pulse with steeper leading and the trailing edges broadens more rapidly with propagation because such a pulse has a wider spectrum to start with. Right? Why? The same thing, right? They have broad spectrum.